Hi, everyone. Welcome back to the seminar. Today, we are very excited to have Chara Podimata speak in our seminar. Chara is currently a FODSI postdoc at UC Berkeley, and she will join MIT Sloan as an assistant professor of operations research and statistics in the upcoming fall. She received her PhD from Harvard, where she was advised by Yilin Chen. And during her PhD, she also interned at Microsoft Research and Google. And her research is in social aspects of computing, and more specifically, the effects of humans adapting to machine learning algorithms used for consequential decision-making. And today, she's going to tell us about information discrepancy in strategic learning. All right, take it away.
Thank you, Said. Thanks everyone for being here. Again, I'm Chara. I know my name is hard to pronounce sometimes, so I think the easiest way to just drop the C in front of it and just read whatever follows. This is joint work with wonderful collaborators. You have Bekavod, Stephen Wu, and Jubaziani. Some of them are in this call today. To set up a bit the expectations about what my goals are for today. My goal is to introduce to you a different model for strategic learning or incentive-aware learning. Then I want to introduce to you some measures of what we think is important to consider in this area, and show you some theory and some experimental results. And I want this to be as much of a discussion as possible. So feel free to interrupt me throughout my talk. It's okay if I don't go through all of my slides. I think it's much better if we have like a discussion around these topics. Okay, so I'm sure most of you in this audience know that machine learning algorithms are increasingly being used for consequential decision-making nowadays. And I know I'm preaching to the choir here, but a machine learning algorithm may decide whether we qualify for a loan or not, whether we will get probation, whether after applying to a job and getting an interview through a video interview software, we will be invited for an on-site interview, and whether students will be admitted to the colleges of their dreams. Now, because these decisions are so consequential for our lives, humans oftentimes try to change the data that they feed into these machine learning algorithms that make these decisions in an effort to obtain better outcomes for themselves. So for example, in the loan approvals case, we see that people try to increase the number of credit cards or bank accounts that they have when they are applying for a loan, or they are trying to improve their credit history with different ways. When it comes to the school admissions problem, students may try to improve their GPA with various means, like retake the GRE, pay for tutoring classes. And an interesting action that we've seen recently is that a lot of students are trying to change schools in order to obtain a better in-class ranking. And of course, similar examples exist in the video interview software, where people try to dress a certain way, they try to hide piercings and tattoos and change the way that they talk in an effort to be perceived as different demographics, so that the algorithm does not bias against them. And I'd like to point out at this point that although I'm talking about, and I will be using the language of strategizing, you should really think of these like changes in the data that people feed as adaptations. People adapt to the algorithms that make decisions for their lives. And these adaptations sometimes help you improve inherently your qualifications. Like, for example, when you actually improve your credit history. But sometimes these adaptations don't change your inherent qualifications, and they're just efforts to manipulate the algorithms. So what is the problem in this general area? The problem is that if machine learning algorithms that are used for making consequential decisions ignore this strategic or responsive or adapting behavior from the side of the people, of agents, we risk making policy decisions that are incompatible with the original policy's goal. And this is what I studied generally in my research agenda in incentive-aware machine learning, where I try to understand the effects of this type of adaptation, both to institutions and society as a whole, and then subsequently try to propose ways for machine learning algorithms to adapt to this type of behavior, not only suppressing manipulations, but also helping people, incentivizing them to become inherently better and more qualified with respect to these algorithms. So just to give you an idea of this whole area, every time that we talk about an incentive-aware machine learning system, I want you to have in mind that there are three key stakeholders that are affecting the way that how decisions are made. On the one hand, we have the institutions. Institutions can be the algorithm or mechanism designers who deploy the algorithms that are going to make decisions for people's lives. Their goals are various. They can strive to increase their profits. If we're talking about the justice system, they want to make more just decisions and so on and so forth. And the actions that they take is that they deploy learning tasks for accurate prediction. The second stakeholder is individuals. These are the people, the data providers, who are going to supply their data to the machine learning algorithms in an effort to obtain the better outcomes for themselves. And the actions that people take is to change, as we saw in the examples in the previous slide, change their data somehow in order to obtain better outcomes from these algorithms. And finally, we have society as a whole. Society has like very broad goals. We strive for fairness, we strive for robustness against bad actors, and we strive for an increase in social welfare. And the action that society can take is, again, like very broad. We can put public pressure on the institutions about what exactly they can do. We can create norms and expectations. So my research tries to kind of like think about these three stakeholders from the perspectives of the three different stakeholders. And some contributions that I've had here, just to give you an idea, is first the paper that we're gonna talk about today, where we study essentially the societal effects of non-transparency in these incentive-aware systems. And then when we talk about the institution perspective, I've worked on creating algorithms that suppress bad strategic behavior from the side of the agents. So whenever agents or people are trying to hide things from the algorithm, we can create algorithms that are robust to these types of incentives. And a very recent line of work that I'm also excited about is how can we create algorithms that are still robust to incentives, but are okay if we do not have the perfect behavioral model for the agents that we are going to face. And without further ado, let me introduce to you what we mean when we talk about the societal effects of non-transparency in incentive-aware learning. So before I'd like to flash this slide, just to tell you that I'm here today talking about a paper and also my work in this area. There are lots and lots of recent and very exciting work that's currently being written in this area. And I wanted to point out that the perspectives that I gave you on the previous slide basically can help guide you through what are the perspectives that the literature has taken in this area. So we have the robustness perspective, we have the fairness, the recourse and incentivizing effort perspective, and very recently, the causality and performative prediction perspective. So I've been saying this word strategic learning or incentive-aware machine learning. Can I give you a model about what this actually means? So when we talk about incentive-aware or strategic learning, we assume that we have a learner who sits here and is going to be the decision maker. So they deploy a decision-making rule. For example, this rule can be whether you are credit worthy to repay your loan based on the features that you submit to the algorithm. And we have the agents who submit their features or their data to the learner in order to obtain the policy decisions. Now, the standard assumption in this whole literature has been that the decision-making rule, be it a linear regression or like linear classification, or like any other rule for that matter, is known to the agents. And because of the fact that this rule is known or revealed to the agents can then strategically change the features that they report to the algorithm, and so try to gain something out of this. Mathematically, this model goes as follows. This is like a Stackelberg game for those of you who are familiar with the algorithmic game theory perspective. There's a learner who has commitment power and commits to a decision-making rule W from the features to 0, 1. We're going to be thinking about regression settings throughout this talk. Then there's an agent with a feature vector X. These features can correspond, for example, to the credit score, the credit history, the number of credit cards that you have. And this agent observes W, the decision-making rule, and best responds by reporting a potentially changed set of features that maximizes their underlying utility function. And then ultimately, the learner's rule is to minimize, the learner's rule is what we call the Stackelberg equilibrium, which is the rule that is the optimum, say, if you care about accuracy, which is what I have here, is the optimum had you given the opportunity to the agents to best respond. So again, what am I saying here? I'm saying that we assume commitment power from the learner. The learner commits to a decision-making rule W. This is revealed to the agents, and the agents subsequently best respond to this rule, okay? And so the learner wants to choose this rule to be the optimal rule. Had you considered this like feedback loop that's gonna happen? And of course, I've introduced the model here. I'm sorry, if there's a question, give me a second. I've introduced the model here, assuming that we have like a homogeneous population of agents. So all of the agents have exactly the same features and exactly the same ability to change their features. But for the purposes of this talk and what I believe is closer to reality, I want us to be thinking that we're dealing with non-homogeneous populations. And let's just focus on two populations of agents that may have different features, the blue features and the green features, and they also have different movement power, different utilities, the green and the blue one. And there's a question, I believe. No?
May I ask, like, can I think the agent as the institute here, and the learner is the individuals?
Good question. So the learner here is, think of it as like the institutions. The institution, this is like a bank that wants to understand whether you're credit worthy enough to give you a loan. And the agent is the person applying for the loan.
Oh, I see. Also, so it seems not, it's opposite from the reinforcement learning language. I see.
Yes, it's different than the reinforcement learning language. It's more closely related to the language of game theory, which is where my background comes from. Okay?
Thanks.
Good. So the standard assumption, as I said, was that this rule is publicly revealed to everyone. But in reality, institutions rarely reveal their decision rules. And there are many, many reasons for that. There are privacy concerns. There is proprietary software that does not allow us to reveal these decision-making rules. Bottom line is, we make this huge assumption in theory, which says that, hey, like the decision maker's rule is revealed, but this doesn't align with what happens in reality. Instead, what happens in reality is that at best, you receive explanations for some of the rules, for some of the decisions that you obtain, or you just get examples of past decisions. Say, someone from the bank tells you, hey, this person that I'm not going to tell you exactly their demographics, they had this and this and that approximately for their application, and the application went through. So this is where we start off from this work. Our model tries to capture exactly this problem, that the decision-making rule is not known a priori. Instead, what is known is examples from past decisions. So we're saying the following: the learner does not reveal the rule completely, but instead scores some past applicants, okay, and reveals to each of the subpopulations what the applicants, what the labeled pairs of the applicants were. This allows the applicants to build estimates of the decision-making rule. And of course, these estimates can be widely different when we talk about different subpopulations. And based on these estimates, the agents of the two groups end up deciding how to strategically change their features. Okay? So let me just say this again. What we see here is that the bank decides and tells you that, hey, these are like past labeled examples of people who applied for the loan, you end up building a model for the world based on the information that you have. And based on this model, you decide how to strategically change your features. And because this can be like very convoluted, let me just introduce this model to you more formally. The interaction protocol that we will be thinking about is the following. Nature somehow decides a ground truth assessment rule. This is going to be denoted as W star throughout this talk. There's like color coordination. So whenever you see like purple, this is the ground truth assessment rule that nature has assigned. The learner, who is the institution, deploys a scoring or decision rule W, but does not reveal it directly to the agents. Instead, the agents per subgroup G draw their feature vectors from the space of allowable features. And this is like X1 based on the first distribution, X2 based on the second distribution. And then each of the subgroups is given access to a peer dataset. You should think of this as like people in the neighborhood of these agents who have gotten prior loan decisions based on the same bank. And based on this peer dataset, people build an estimate of the decision-making rule, and they decide to report with this altered feature vector X hat of G. Okay? The thing that I want you to take from this slide is that, one, the decision-making rule is not revealed to the agents, and two, the agents do something that is subgroup specific and obtain estimates for this rule. In some sense, this corresponds to the example of people being like, hey, I didn't get approved for this loan. What did you do and you got approved? Like, what was your application like? Okay. I'm going to make it more formal in a second, how exactly they built these estimates from the peer data set. But for now, let's keep in mind that this is the general interaction protocol. Now, what is the learner's goal? The learner, when they deploy the scoring rule, we assume that they try to maximize the social welfare after best responding with respect to the ground truth assessment. So this is the Stackelberg equilibrium that we strive to achieve in this setting. Our learner tries to make sure that when deploying the W and expecting that the agents are going to best respond, they still maximize the social welfare of the agents. So we assume a benevolent principal, a benevolent learner in our setup. I'm going to pause here and take questions on the general model before I delve into the specifics of the model.
I have a really quick, easy question. What does private mean here? Does that mean individual? Or what? Yeah, what does private mean?
Yeah, sorry, it means individual. It's like, and it's hidden from the learner. So it's unknown to the learner. The agents know their features, but it's hidden from the learner.
But the learner knows D1 and D2.
Yes, but they don't know the sampled data point.
So does the learner know like there's like 10 manipulators and then they each get their own draw, and then those are yeah.
So is the question, what does the learner know?
Yes, correct.
The learner knows the distributions D1 and D2. They don't know the origin. They don't know the features XG. They do know the features that are reported to them. So like the X hats. So at some point, they receive a data point.
Yeah.
They know that this data point has been altered through some utility maximization function, and they know that the original population was coming from this D1, D2 distribution.
Oh, yeah. So X hat is what you get when you manipulate. Okay, yeah, thanks.
Yes. And just in case I won't have time to cover this, we basically relax these assumptions in the paper. So we have extensions for which you don't need to know the utility functions of the agents. You don't need to know the populations where they come from. We have an extra learning process through which you can uncover them. But for now, let's think that this is known.
Wait, and so the
Other
learner
questions?
does the learner has any, does the learner have any access to the unmanipulated distribution?
They can know the distribution, but it doesn't matter for them.
Yeah, okay, thanks.
And just so I understand, sorry if you said this already, each population has samples only from their own population's distribution. They don't have samples
Exactly.
from the other. Okay.
I'm about to define this formally. I'm about to define exactly what it means to be subgroups, to have subgroup specific features. But this is exactly right.
Thanks.
Other questions?
What happens if you let F depend on the subgroup? I mean, sorry, let
What
W depend on the sub. Yeah, you have like W1, W2.
Yeah, that's an excellent question. And you're kind of like hinting at things that I wanted to discuss afterwards. As computer scientists, we would like this solution because this is like different, maybe we will be able to alleviate a lot of injustices by deploying different decision-making rules for different subgroups. But this doesn't really fly with policymakers. It's like really hard to argue that like you're gonna use different decision-making rules for different populations. So yeah, that's an excellent question. Oftentimes you just have to use the same rule for everyone.
I'm a bit confused about the relationship between W star and W. Like here, like the learner's goal is to argmax W prime. I guess it is because of the manipulation. So it's implicitly embedded in X hat. Is that? So
good question. And let me reveal the right next point on my slide, which is why are these two different? So why is the decision-making rule that the learner deploys different than the ground truth assessment? Because note, and I want to hint back, this is going to be made more concrete once you see kind of like the math behind how the model is defined. But basically the high level intuition is that oftentimes the ground truth assessment rule does not incentivize the agents to optimally improve their outcomes. And here we want to help the agents increase their social welfare. W star all by itself may not be doing that if the features are unchanged. Think of it as like W star is an oracle, it's a genie somewhere that tells you that if you feed me any feature vector X, I can spit out exactly how much the qualification for this X is. If you deployed W star all by itself, you wouldn't be able to incentivize people to change their features optimally so that they can obtain better outcomes. So what we're trying to do here is we're trying to build a different regression or linear classification thing that incentivizes people to improve their outcomes. And this is going to be made concrete in the next slide or so. Thank you for the question.
Sorry, I promise this is my last question.
Yes.
For you, does U depend on W for this utility function?
Yes, but let me make this more concrete in a slide or two. Okay. So the main question that we wish to address in this work is, how do these information discrepancies that I've started hinting at for the different subgroups regarding the principal's decision rule affect the ability of the agents to improve their outcomes? And to make this more concrete, I'm going to start by telling you, first of all, to Aaron's question, what are the discrepancies when it comes to the feature vectors of the subgroups? So we assume in this work that the two subpopulations live in different subspaces of the feature vector X, and they're defined by the supports of D1 and D2. And I'm going to be using pi1 and pi2 to be the orthogonal projection matrices onto the subspaces S1 and S2. This basically means that that there's a feature discrepancy between the subpopulations. This is what Aaron was asking about, whether each subgroup sees features from the other subgroup or not? The answer is no. Each subgroup only has access to their own features. And x of g is essentially equal to pi g of x of g, because they live exactly inside this subspace. They don't move outside of this subspace at all. Now, moving on to the subgroup utilities, which was Kevin's question. The utility of subgroup G of an agent with point feature vector xg, if they were to report x prime, is equal to the difference between the estimated score that they think they will obtain with x prime minus the cost for moving from xg, which is their true feature, to x prime. Again, what is this quantity here? This is the score with that they get with their estimated decision rule. Because remember that somehow these agents are given access to this peer data set, and through this peer data set, they build estimated decision-making rules. They have an estimate for what the algorithm really does. And to be more concrete, the dependence between the estimated score and x prime is linear. So the utility of the agents is x prime, inner product with the estimated rule, and the cost is essentially this like L2 norm. We're gonna think of these as like different cost matrices that scale differently how the features move.
And sorry, one question. I want to understand how.
Yes.
I want to understand how different subspaces is sort of going to be a different or stronger assumption than just saying that they have different distributions. So is the assumption that the supports are disjoint, for example?
They don't have to be disjoint, but they're different. Like some of our results essentially. Say that again.
Sorry, like, do they have to be different, or just they can be different?
They can be different, yes. So our results, the results that I hopefully will have time to present. This paper is like a study on what can happen based on the different subspaces. So we have some results about what can happen if the subspaces are identical, if the subspaces are overlapping, if the subspaces are completely orthogonal.
Got it. Thank you.
Of course. All right. Okay. So we saw previously that this, oops, why doesn't this move? Yeah, we saw here that the agents somehow need to understand how to best respond based on this like estimated rule that they have. So how do they build this estimated rule? Now, from the perspective of each agent, for the different groups, this is going to be our blue group and this is going to be our green group. The agents have access to labeled examples from their peer subgroup. These labeled examples have to do with the decisions that other applicants have gotten from their own subpopulation. And based on these like examples, each subgroup builds their own estimator for the linear regression that the decision maker runs through running a simple ERM. And also we are going to assume that our agents are risk averse. So they don't just, they try to hedge as less as possible. So not too much. Okay. So again, what do we learn here? We learn that the agents obtain access to this peer data set. And on the peer data set, they run an ERM process to try to recover what the estimated rule for the decision maker was. And if you do the math here, you end up seeing that essentially, because of the way that we have set up the axis of the where the subpopulations live, the estimated rule for each subpopulation G is equal to pi G of W. So at a high level, it's equal to the projection of the decision maker's actual rule on their own subspace. And this is a byproduct of what Aaron asked like 2 questions ago, that the subpopulations do not have access to features from the examples from the other subpopulation.
Sorry, and
Yes.
one more. So I'm a little
Yes.
confused by this because I would have expected both that there would be sort of like finite sample approximation error, and also that there would be ambiguity about what the decision rule was. There might be multiple, even on the distribution, there could be multiple half spaces consistent with the same set of observations. So how do those?
Yeah, good and acute questions. There may be multiple half spaces, but we assume that the agents are risk averse. So by risk averse, we essentially mean that we're going to minimize we're going to choose the half space with the minimum norm, so that we don't make any. Yes.
Okay, and okay, so that's a sensible rule.
Yes. That's for your second question. For the first question, I have a different answer.
Okay.
For the first question, which has to do with like finite sample, I'm abstracting away a lot of things here because I want it to be clear. So we do require that there's access to at least a number of samples so that we have good approximation guarantees. And we also do abstract away from errors in the procedure, in the sampling process, by assuming that essentially like there are no errors when you obtain the classification for these. Like it's a realizable setting essentially. But if you had errors, these would like propagate throughout.
And no overlap. Oh, I guess this is Aaron's question. There's like no group overlap, really.
There can be group overlap, but it's like it's just one of the cases.
Okay.
The group overlap will be based on conditions on the projection matrices, pi 1 and pi 2.
Got it. And just one last question. So how come
how
come the minimum norm solution corresponds to risk aversion?
Good. Because you wouldn't want to, so the way that we thought about this was that, well, we really don't want to assume that one feature has more information than other features. So by taking the minimum norm, we were like, yeah, that's like kind of like the best information that you had at this point.
Okay, thank you.
Sure. Any other questions? Cool. So if the agents best respond according to this process that we said before, and again, just so that we're all on the same page, the principal deploys a rule, decision-making rule W. Agents obtain some label data on which they run ERM. And then based on these data, at the second stage, kind of they best respond and they report their data to the principal. So this means that essentially, based on how we define the utility function, the agents maximize this like pi g of w x prime, this inner product, minus the cost for moving from x to x prime. Okay. And as a reminder, this is the estimated score that you will obtain by the principal's rule. And this is the manipulation cost or movement cost. And because of the way that we've set up this example, we can actually solve this and obtain the closed form solution. So we do know that for for agents of the subpopulation G, the reported point is xg, which is what they started from, plus a movement term that we call delta G of W. And this movement term depends both on the cost function based on the cost matrix that this person had, and also the estimated rule that they saw from that they estimated from the principal. Based on this, the principal can actually compute the closed form solution of the decision-making rule that optimizes their social welfare. And this closed form solution takes this form here. So it depends both on the two subgroups in pi 1 A1 inverse plus pi 2 A2 inverse W star reweighted so that it's norm 1. And if we think about this term here, I want to now think about more to this question that June had a couple of slides before why is it true that W, the social welfare maximizing rule, is different than the ground truth assessment rule? And the answer here is twofold. First of all, there are cases where the two rules are exactly the same. What is such a case? Such a case is when the two subpopulations, A1 and A2, have exactly the same cost matrices. They are identity. And also when the two projections recover exactly the whole space. So that's one of the cases where you can see that the social welfare maximizing rule is equal to the ground truth assessment rule. But in general, this is not true. And the two quantities here that kind of like give us the equality are the reason why this is not true. So this is not true in general because you can either have disparities in feature modification costs, so these like AG matrices here, and this means that it may be worth incentivizing feature changes that benefit both groups instead of just one of the two groups. And I have a concrete example here where we have the W star being 2/3, 2/3, 1/3. This is like the ground truth assessment rule. The projection matrix for the first group is just 1, 0, 1, and for the second rule is 0, 1, 1. So this means that the first group essentially has access only to features 1 and 3, and the second group has access to features 2 and 3. And if you go through this process that I had before, you can compute that the change in the social welfare, if you were to deploy W star, so the ground truth assessment rule, would be 10/9. But if you were to deploy a rule that significantly favors the third coordinate, then you would end up having an increase in social welfare that's strictly more than 10/9. And I believe there are two questions. There's a question. In the full information setting and no feature discrepancy, should you publish W star? If there's no feature discrepancy, then it means that pi 1 and pi 2 are exactly the same. And by full information, you mean that the principal knows everything?
Yeah, the agent knows W star.
Yeah, but if pi 1 is equal to pi 2, but feature modification costs are different, then it's still not the case that W is equal to W star, right? Like you have to make, how do I close this? Yeah, see, in this equation here, if pi 1 is equal to pi 2, and the cost matrices are still different, it may be the case that you need to incentivize different things.
And let me ask something that maybe I missed about the model before. So these subspaces, is it that they're not just telling us where the sort of true features lie, but that the subgroups are constrained to playing modifications that also lie in those subspaces?
So the second is an implication of the first. So the groups, the original features, do lie within these subspaces. But because of the fact that each subgroup only has access to peer datasets from its own group, it ends up being the case that they are constrained into also moving also within this subspace.
Okay, you're saying because the minimum norm solution will zero out things as
Exactly.
and so I guess the samples they're getting are like the unmanipulated samples from their population.
Yes, exactly. Yes.
Okay.
Okay.
Yeah, thanks.
Sure. So, okay, what have we done so far? We've set up the model. We hopefully have a clear understanding of what are the components of what the players or what the agents are optimizing for and how they're optimizing for these solutions and how the learner chooses the social welfare maximizing solution. So what do I want to measure in this problem? Well, what I want to measure is what we call the outcome improvement in equilibrium, which is defined as the how big your outcome is based on your ground truth assessment rule after your best responding, minus how big your outcome was originally. Okay. And so how am I going to judge whether outcomes are improved correctly or appropriately or whatnot? Like, what are the questions that I want to address with respect to this outcome improvement? The first question that I want to address is, are all individuals better off by participating in this interaction with a principal? And we call this the do no harm paradigm. The second question that I want to address is, how big is the total outcome improvement that these individuals are able to obtain? And the third question is what we call the per unit outcome improvement, which essentially is a measure for quantifying whether effort is exerted in the optimal direction based on each subgroup. So to be more concrete, if you can write out exactly this x hat of W as I showed you before, which is the x, the original, plus the delta G of W, you end up seeing that the improvement for group G, if the learner were to deploy decision-making rule W, is equal to the inverse of AG, the cost matrix, multiplied by pi G of W, which is the estimated rule that this subgroup has, inner product with W star. So the question that I want to first address is, are all individuals better off? In some sense, this is the way that I think about this is like the bare minimum. When we ask people to participate in these settings and they adapt their behavior to what the algorithms do, and especially given the fact that the principle is a benevolent social welfare maximizer, we should be making sure that all individuals are better off. And surprisingly and sadly, for general costs and projection matrices, this is not the case. And we have counterexamples in the paper where it will end up being the case that one of the subgroups ends up being clearly disadvantaged even after participating in this setting. And the high-level intuition as to why this is the case is that there can be contentious information from each group, which combined with weird cost matrices can make sure that despite the principle still maximizing for the total social welfare, one of the subpopulations is clearly worse off. Now, luckily, there are several notable examples that we don't fall into this problematic case, that we can guarantee that we have no negative externality by participating in this setting. And some notable examples are when the movement costs for different populations are proportional to each other. So when A1 is C times A2, where C is some constant, or we don't have interfering information. So pi 1 and pi 2 are orthogonal to each other. The second question that I want to address, as I mentioned, is by how much can we guarantee that there is total improvement in the two groups? And is it ever equal? First of all, we prove a result that says that when you focus on two groups, the difference between the outcome improvement that they obtain for a decision-making rule W is upper bounded by something that we call the information overlap proxy. This quantity here is the projection of the ground truth assessment rule, and I'm sorry, this should have been purple for group 1, minus the ground truth assessment rule projected onto space 2. So this information overlap proxy in general, it's not tight, but there are some cases where this is tight. So when the information, the difference between the two improvements, outcome improvements, is exactly the L2 norm of pi 1 W star minus pi 2 W star. And there are the conditions in the paper, they have to do with the collinearity of the pi G W stars. And not only that, but we can guarantee that there always will be equal outcome improvement if and only if the inverse of the cost matrix for group 1 multiplied by pi 1, and again, the inverse of A1 is equal to the inverse of A2, pi2 inverse of A2. So to think of this more simply, think of it as like a notable subcase is when A1 and A2 are the identity matrix. They're both the same. So you don't need to think about them right now. So you can obtain equal outcome improvement if and only if pi1 is equal to pi2. Okay. But it seems that when we were thinking about these questions, it seemed that it was a bit unfair to think about equal outcome improvement, because it may be the case that the subpopulations start off by very different outcomes. And so we should really be making sure that the subpopulations do the best that they can with respect to their ability to move. And this is what we try to capture by quantifying what we call the per unit outcome improvement, which is defined as the improvement for group G if the decision-making rule was only projected over their subspace. Okay. And I know this may seem weird the first time that we take a look at it, but it has several interesting properties, the per unit improvement as a measure. First of all, it considers only part of the decision rule that belongs in the relevant subspace for each group, as we said. And secondly, it measures how efficient the direction of this rule projected onto the subspace for the subgroups is for the improvement. And the nice thing is that here there is a notable example for optimal effort exertion, namely when there is non-interfering information and the two subspaces are orthogonal, then we can achieve at least the optimal per unit improvement for all of the groups simultaneously. And because I don't have a lot of time and I want to leave time for questions afterwards, I won't go through our experiments. I just want to briefly say that we had experimental results that we ran on two very well-known data sets. Basically, what we did is our experiments are semi-synthetic. So we separated subpopulations based on different characteristics that we thought made sense. And then we tried to predict the income improvement as a model, as a mode of essentially outcome improvement in this case for each of the subpopulations. And the experiments that we had essentially validate the theoretical results that I showed you earlier on. I won't go through that. I want to summarize and say that when there exists information discrepancy in the decision-making rule among subgroups, what we saw in this talk today was that in general, it can be the case that not all individuals are worse off. But luckily, there are cases where, for example, when you have proportional movement costs or non-conflicting information between subgroups, you can guarantee at the very least that there is no negative externality for people participating in this setting. Then we saw that not only that, but we can also have equal total outcome improvement whenever this condition with the cost matrices and the projections holds. Essentially, if the cost matrices are exactly the same for the two subpopulations, this is true when pi1 and pi2 are exactly the same. So the two subpopulations live on the same subspace. And luckily, this measure of per unit outcome improvement tells us that effort is exerted optimally for each of the subgroups when there's like non-overlapping information, or you have proportional movement costs and pi1 is equal to pi2. I want to briefly mention some extensions that are included in the paper in case you're interested in finding out more about this. I briefly said in the first slide that although we consider the full information static case, offline case here, in the paper, we generalize this to the principal's learning problem when the pi g's, the a g's, and w star is not known a priori to the principal. So the principal has to have an extra learning component in order to figure out these things. We also have generalization, like we presented generalized results for more than two groups. I just kept the two groups presentation here for clarity. And sorry, I can't read this last thing because, wait. Yes. We also have an extension where the principal does not just care about social welfare, but they care about a combination of accuracy and social welfare. In the 2 remaining minutes that I have, so that we have like 2 or 3 minutes for questions, I want to tell you what my broader vision for this area is. And those of you who heard me give my job talk last year have already heard that, but I felt that this is a more concentrated audience, so I wanted to plug this idea for you too. So whenever we talk about strategic or incentive-aware machine learning settings, as we saw earlier in this talk, we usually think of the rule as being known to the agents. And because of this rule being known, the agents strategize and they change their features. So it seems that we're having like 2 very opposing viewpoints. On the one hand, we have the viewpoint that says that we should create obscure machine learning algorithms, non-transparent algorithms, that they have the plus that they stop strategic behavior altogether, but of course they're non-transparent. On the other hand, we have the completely opposite viewpoint, which is closer to where I come from, which says that no, algorithms that are involved in decision making should be made public and hopefully be tuned in a way that incentivizes efforts for outcome improvement and somehow try to not be as prone to strategic behavior. I think what we should spend more time thinking about in the coming years is algorithms that are interpretable to an extent by the agents, so as to incentivize the agents to exert effort towards outcome improvement, but they're not exact enough, they're not accurate enough, so that the agents can engage in this bad manipulating strategic behavior. And the way that I view this shaping as a research area in the next couple of years is the following. If we think about the timeline of where we are right now and where we want to reach, I think the first questions that we need to address is what happens when learners have nonlinear rules. For example, rules that are coming from neural nets or from complex decision-making algorithms. And we can play around and understand what happens if agents understand these rules and fully best respond, or approximately understand them, or don't understand them so much. The next thing, and I think this is very important, despite the fact that we are a theory audience here, is that it seems that there needs to be the case that we talk to practitioners and create case studies based on how these rules, these algorithms are actually deployed and how people actually respond in practice. And although I don't have any concrete work here to talk to you about, I gave a tutorial with Yo Shabit and Ben Edelman at Fact 21, where we tried to break down the perspective of, the theoretical computer science to policymakers and lawmakers in this area, so that we can try to establish common grounds and a dialogue between the communities. I think that finally, the holy grail would be these like interpretable algorithms that are robust to strategizing and to incentivize honest outcome improvement. But of course, there are many steps to take until we reach that point. And with that, I would like to conclude and thank you all for being a wonderful audience and for your excellent questions.
Do we have any questions? If you do, then unmute yourself and ask.
It's okay if we don't have questions. I think we had a good discussion throughout. Oh, we have one in the chat. Oh, no, it's not a question. Sumega.
I have one high level.
Hyping me.
I have one high level question. Like, is there any connection between this domain and the field that studies distribution shifts? Like, once you deploy a classifier, it changes the distribution of the data in the future, or maybe it's called like performative prediction. Like,
Yeah, so all of these notions are related, and I think that we need to be careful here that these are ideas that have emerged from different communities. So from the game theory community, this is known as like response dynamic, is known as like Stackelberg equilibrium and Stackelberg games. It's very similar to what happens in performative prediction, where essentially what you do induces changes in the data points, and also distribution shift. The only difference between distribution shift is that distribution shift does not explicitly model the utilities of the agents and how these affect the adaptation of the data.
I see. So it's more from a machine learning perspective, not including the game theoretic aspect of it.
Yeah. There are connections though, like even in the performative prediction, the very first paper, essentially the notions of performative stability and performative optimality, they're very, very related to notions from Stackelberg and Nash equilibrium. So there are definitely connections.
If there are no more questions, then
I have a general question. So the goal with social welfare is just to increase qualification, but don't we also care about the total cost invested?
Yeah, that's an excellent question. We haven't modeled it in this work, but you're perfectly right. Like it's actually one of the very good open questions. Like, what if you want to balance out the increase in qualifications given the minimization of cost for the different groups? Yeah.
Thanks.
It's the same problem that we're having with many settings in this area. Like, we cannot optimize simultaneously for everything. I can see a very good argument in favor of optimizing for qualifications, but I can also see equally excellent arguments for optimizing for the cost exerted.
Thanks.
Of course.